Hello there, Nick and Josh here, and we're here to talk to you about our solar panel mount. The first thing to take into consideration, our plants can be characterized by their heliotropism, that is, their tendency to grow towards sunlight. A solar panel, much like a plant, will produce its greatest output while its face is perpendicular to the rays of light from the sun. Thus, it is desirable to have a solar panel that functions heliotropically throughout sunlight hours by driving the panel with a motor.
Through research of how sunlight varies throughout a single day and by season, it was determined that an equatorial solar panel mount with 2 degrees of freedom would be ideal. 1 degree rotates the solar panel throughout 170 degrees of motion during sunlight and back to its starting position overnight. The 2nd degree allows the mechanism to be adjusted seasonally, an idea we will return to. The mechanism meets all design criteria that were established. It's driven by a rotary input. It accommodates a 65-inch by 39-inch solar panel without taking up excessive space. The 4-bar linkage used is Grashof, meaning the solar panel is able to rotate throughout its range of motion without being over-constrained. And lastly, only simple pin joints are used in the design.
Geometric synthesis was used to coordinate the motion of the mechanism based on 2 rocker output positions and a desired angular displacement of 170 degrees for the solar panel. With these specifications made, a coupler length of 40 inches was chosen to ensure sufficient clearance between the solar panel, the linkage, and the motor. The resulting 4-bar linkage was built in GeoGebra to verify the location of ground link 02 and to illustrate the range of motion of the rocker and consequently the solar panel.
In addition to the repeated daily rotation of the solar panel, the mechanism has the ability to rotate the solar panel through various angles of inclination based on the season. This is done through rotating a component we will call the pivoter, which is labeled with 3 orientations for winter, fall and spring, and summer.
The solar panel can be seen oriented at midday for each season. It should be noted that the component in charge of inclination, or the pivoter, is fixed by a simple lock bolt and can be easily changed for additional orientations, say on a monthly basis if desired.
The mechanism's toggle positions were designed such that they would correspond to the desired positions of the solar panel at sunrise and sunfall. As mentioned, both GeoGebra and the SolidWorks assembly of the model were used to ensure that the mechanism could reach these start and end positions without issue.
The maximum and minimum transmission angles were identified as 89.7 degrees and 2.31 degrees respectively. This maximum transmission angle is optimal in that it will maximize the tangential force applied between the links, which is all used to produce output torque on the rocker. It would have been ideal to keep the minimum transmission angle above 40 degrees to provide this same advantage. However, the torque applied to the output rocker is not the main concern.
Looking at the panel orientation angle throughout the motion of the crank, the peak panel orientation, representing sunfall, occurs at a crank angle of about 180 degrees. This relationship allows the solar panel to follow the sun for 12 hours of daylight, which is typical in March and September, before returning back to its starting position throughout the next 12 hours. The exponential relationship on the back half of the movement can be disregarded, as it doesn't affect the time to get back to the start position. Still, the downside of this mechanism function is that it won't fully take advantage of the sunlight in the 5 months of the year that see more than 12 hours of sun each day. A quick return mechanism would be a good solution for this deficiency.
In this brief demonstration video, we are able to see how our solar panel mechanism operates. We can see the electric drive motor input a constant rotation and watch how the mechanism turns the panel in the proper oscillatory motion to capture the sun's rays. We can also see the angle of inclination change to demonstrate how this would operate year-round. Well, that concludes our overview of our solar panel mounting project. It's Josh and Nick again, and we'd like to give a special thank you to DJ Quad for the background music. Thank you and have a good day.